at the parts of the microscope, right? There were a few of them that we wanted to remember. Remember what those were?
Arm.
An arm. Does anybody want to draw a microscope for me? Oh, you glad you made it. Come on. Oh, hi. Let's see it. There you go. Give somewhere over on the left side of our screen then. Well, you can label as you go, or we can get other people to label them for us, or however you want. You're in charge now. Nice. You want to keep going? I'm not sure how the top part is connected to the bottom part, but that's okay. I'm sure that everybody can work that one out. You see what I'm talking about? What's the top part called? The ocular lens. Yeah. And how is it connected to the bottom part?
Like that.
Yeah. Oh, no, there we go. Now it's all connected together. So okay, so we got the ocular lens up on the top, right? So maybe throw a label on there for us. Ocular lens. Good. We also call the ocular lens the what? Where?
In lens.
Oh, I think there's different spellings. I think it's like, I don't even know. This is normally how you'll see it spelled. I think if you put an E on the end, it might be British. I'm not sure. But anyways, put an E, don't put an E, doesn't matter. I know what you're talking about, right? So ocular lens, what else do we call it? The eyepiece, right? The eyepiece. Because it's where you stick your eye.
Oh,
What else we got?
objective lens.
Objective lens. How many of those do we have?
3.
3 of those. Objective lens. Going in. Down a little lower for us there, Nayan. Can you put the arrow down below? Yeah, there we go. Those are the objective lenses there, right? That top we actually call it's called the rotating turret. Oh, we didn't have to know that one. And then what else? Arm.
Stage.
Stage.
Course. Knob.
Stage.
Course.
Course. Which one's the course? The big one or the small one? The big one is the course what? The course adjustment knob, yeah. Something good? The course adjustment knob is the big guy, and the little guy is the fine adjustment knob, yeah. So, you're okay, just watch that button. Ah! Which one is that? That's the fine adjustment knob. Yeah, right. And what's the difference between the coarse adjustment knob and the fine adjustment knob? When would we use one and when would we use the other?
The coarse adjustment knobs move the stage and make movement.
Yeah.
And the fine adjustment knobs like move it like slow, like
Focus.
Yeah, so why would we use one and then the other? Like why would we want to move the stage a lot?
move it so that we can see something.
Okay.
And then we'll focus it.
Yeah, use that coarse adjustment just to find it, right? The whole idea is that a microscope works with like a depth of field, so it only sees a particular visual plane, right? So it only sees these small slices through air in clean focus. So you use the coarse adjustment knob first to move it up and down to find it, to get it somewhere close to that focal plane, right? And then you use the fine adjustment knob to really focus in and to get that crisp detail so that you can see what's going on. Nice. We're missing one. Well, 2, I guess.
Base.
The base and the
Light.
light source. Yeah, there we go. So there's our light. And then the The big hulking brute on the bottom is the base, yeah. And why do we care about the arm and the base? Yeah, because that's how we carry it around, that's it. Otherwise, we're not too concerned, right? They're not really doing anything for us as far as the actual visual aspect. I mean, the arm is important because we got to keep the lenses and the light source and stuff away from each other. But generally, we want to be carrying stuff along. Awesome, thank you very much. Good. So, ocular lens and objective lens, what are they for? They're magnifying the image, right? They're magnifying whatever the specimen is. So rather than us just looking at it with our bare eye, our naked eye, right? We put it underneath those lenses, and lenses are going to make things appear larger, right? So, anything else? What's this guy for?
Putting the stuff in.
Yeah, that's where we put the slide, right, with the specimen on top of that. And it just holds it. So basically what we're trying to do, I was just talking about the focal plane, we're trying to make our focal plane right here on top of the stage, right? If you move this guy too low, so usually our stage is attached to this thing, right? There's a microscope, one of those microscopes that we'll put away. We don't have any around. But you can sort of see the same thing, right, on our stereo microscopes over here. You guys just pass one of those in to me. Thank you. Right? So if we're looking at one of these guys here, it works similarly, except this time we're going to put the slide right on the base, right? There's no stage in this one. We put it right on the base, but something's still going to move. Somehow we've got to get the focal plane right. So our adjustment knob now actually moves the entire setup on top, right? But it's the same idea. It's just making the lens closer to wherever you have the specimen, right? Or farther away. And that's all. So that what we're trying to do is we're trying to get everything in the focal plane so that we can see it with good detail. And that was a good demonstration. Good. If you're into photography, pretty much got focal plane worked out probably. Anything else? We okay there? Move on to the hard stuff, which hopefully isn't too hard. Good. Okay, so we were talking about our objective lens and our ocular lens, and we were talking about the fact that these guys are related to magnification. What do we use those guys for? Like, how do we use those to figure out different things? Say again? Somebody, no? We've got objective lens, we've got ocular lens. How do those sort of combine to give us total magnification? Just multiplying them by each other, right? So total magnification is equal to what? Ocular times objective, right? Right, so our ocular lens always stays the same, but our objective lens, we can change it. Right, it can rotate around, which means that we get different total magnifications. Right, so if our ocular lens happens to be 5 times, and we have the same lenses that we have on ours, so we have, remember what our 3 different objective lenses are? We have 4, 10, and 40. So if we were using the 4 times objective lens with our 5 times ocular, what would our total magnification be? 20, right? 5 times 4. If we were using our 10 times objective lens, it would be 50 times total magnification. If we were using our 40 times objective lens, it would be 200 times total magnification, right? So if you look through the microscope on the high power objective lens, right, through a 5 times and your 40 times high power objective, the image that you're looking at is 200 times larger than it appears if you were just holding the slide up and looking at it from the same distance with your eye, right? Which is pretty amazing. These things are pretty wild, right? And the discovery of microscopes completely changed our understanding of science, right? I mean, when we were like, I don't even know, what was it, 200 or 300 years ago? Who was it, von Leeuwenhoek or something? Don't quote me on that one. But he figured out that we could look at really tiny things. I think we had telescopes already, and he went, well, wait a second, what if we sort of turn this around and look in the other direction, right? Or not turn it around, but change the shape of the lenses and put them together, and all of a sudden we saw this world that didn't exist to us, right? We're like, well, why do we get sick? And we went, oh, there's all kinds of crazy little bugs that are cruising around that nobody even knew about, right? Because we just had no idea. So they changed our total understanding of science and of biology especially. So, total magnification, this one, any questions with this one? Pretty easy with this calculation, we're good? Okay. Then the tricky one, what if we want to calculate the size of an image? Okay. Where do we start? If we look through a microscope and we see something, how big is it? Right? So this is, these original scientists are kind of going there, they're looking through, right? And they're checking out their microscope, their early microscopes, which kind of look a little bit like telescopes, right? And they're looking and they go, oh wow, there's something. Hey, where'd it go? Oh, there it is, it's back again, right? How big is it? Like I can't see it, it's not there. And then they look through their microscope and it appears, right? They're able to see something that's incredibly tiny, but they have no idea how big it is. So what sort of strategy do we use to figure that out? Zach, come on, that was kind of a hand one. If you want to help us out. Yeah. Don't
They put like a ruler underneath the microscope.
Okay.
Make the field of view.
So first we got to know the field of view, right? First we have to know what's the size of the space that we're looking at, right? So first we've got to calculate field of view. Whoa, that's not working at all. There we go. Field of view. Okay. Of what?
Of the smaller magnification.
Of the smaller magnification. Okay, so we're going to take our small magnification. So we know the field of view of the small magnification. So we're going to actually measure that field of view of, come on, there we go, of what? Of lens X, we'll say. Right? And we're going to measure that. Does everybody know what I mean, like the difference between a measurement and a calculation? You guys know sort of when we talk about using those two different terms, like what's the difference between a measurement and a calculation? Keep going.
Measurement is something that's just very straightforward, like, oh, I measure this and it's this long or whatever.
Okay.
And then a calculation is where you take two measurements, or more than two measurements, and figure coming out with them.
And you start combining them together. Yeah, exactly. A measurement is something that you physically take, right? So I can measure this table, I can put a ruler down on top of this table, and I can measure the table. Right? I can measure the length of the table, and I can measure the width of the table, but then I can use those two measurements, and I can undergo a calculation, and I can calculate area. I could also measure area. How would I be able to measure area? Keep measuring what? What do I have to have in order to measure area? Like in order to measure length, I've got to have a ruler or something because it has centimeters, which is a unit of length, of distance. But if I wanted to measure area, what would I need to have?
Square.
Yeah, and I have to have like a little square, right? I'd be like, okay, I know the area of this book is whatever. Let's just say it's 1 square unit, whatever that is. And I go, okay, it's 1, 2, 3, 4, and I can actually measure how many square units that is, right? I could measure area in that sense, but we usually don't have square measurement tools like that. Right? So we field of view of lens X, we're going to go ahead and measure that. Once we've got that measurement, okay, then we know the field of view. So now what do? How do we calculate if we're using a microscope, right? And we can figure out how big that is. How do we figure out the specimen now?
So you take your other objective?
Hold on, wait a second. Let's just go with figuring out the size of the specimen at this lens.
Then you just compare it to the field of view. You see how many times it fits in.
See how many times it what?
Fits in.
It fits in. So if you're going to make that into or turn that into a calculation, what is it that we're calculating? Or how do we calculate it? Field of view divided by fit number, right? However many times it fits. So the size of our specimen right, equals the field of view divided by the fit number. Right? And our fit number is just what? into the space, how many times the object fits into the space, right? So if I wanted to figure out how long this power bar, power strip thing is, right? And I don't know how long this is, but maybe I know that this table is 1 meter long, right? Then I take my 1 meter, which is equivalent to my field of view, right? And I just find how many times it fits. And I go, okay, there's 1 of those. That would be 2. So it would fit about maybe 2 1/4, right? Approximately. So I would take my field of view, which is 1 meter, and I divide by my fit number, 2 1/4, right? 1 divided by 2 1/4, and it gives me the number of meters long that this thing is. Yeah? Does that make sense? And you can do it the other way around too, right? If you know that you have, what do you guys have, like a 13, 15-inch screen on your computers? You guys do computer screens in inches or centimeters? Inches, yeah, I've always done in inches, eh? But if you know you got a 13-inch screen, you guys know how they measure screens? Just like the length of the screen, is it the width, is it the height? You don't even know? Maybe you guys buy computers all the time. The width? No, it's the diagonal. You always measure the diagonal because it makes it look bigger, yeah. Usually the diagonal is the same thing, right? So if you're looking at this guy, right? Where's my big trusty ruler? Right. We want to measure how big this screen is. We go corner to corner. We find that that's what, 35 centimeters approximately, right? I don't think we have inches on here. No inches, sorry. Right? Divide by 2 1/2. You're probably looking at 13-inch screen. 13 times 2 1/2, 26, and half of 13 would be 7 1/2. 33 1/2. We're pretty close. Anyways, sorry. Right, the whole idea though, the reason I was going to say that is that you can go the other way. So originally we knew the fit number, right? Or sorry, we knew the field of view, and we could, knowing the fit number or measuring the fit number, we could then calculate the size of the image. Well, we could go the other way around as well. If we know the size of the image, which doesn't happen very often when you're using a microscope, but if you happen to know the size of the image, right, then you could calculate the field of view just doing the reverse calculation, right, going the other way, right? We could take Sabrina's screen and we could put the screen down across the table and we could go, oh, the screen is 33 1/2 centimeters long. Okay, now I can calculate the total length of the table, right? So all these calculations can go in both directions. Yeah? People awake right now? Not awake right now? Does no response mean awake or not awake? Awake. You are awake. Okay. We got, what, 6 minutes. So, if we now know how to calculate, or we know how to measure the field of view, and then we know how to measure the fit number, and we can use those two things to calculate the size of the image that we're looking at. What if we need to increase magnification or decrease magnification? How now do we go through the process? So if we know the field of view at the low power on our microscope, but the low power is actually sort of too small for us to look at. It's not magnified enough to look at whatever we're looking at. So we increase to a higher power lens. How can we now figure out what our new field of view is? By Dominique, keep going.
Field of view times the smaller magnification over the larger magnification equals the other field of view.
Okay, so the field of view of the lens that we know, so let's just say that we're going to take field of view of lens X, right? Why don't you want to work? There we go. Field of...
I think it has to be on the left side of the
I
board.
know, it doesn't seem to like me the other way around this way, does it? Field of view of X multiplied by... It really doesn't like me. Okay. Field of view of X times what? Times the magnification that we're looking at, right? So the magnification of lens X
Divided by the other magnification.
divided by the other magnification. Yeah, the other magnification is probably the one that we're gonna know, right? Because usually we're trying to we have to find out the field of view, right? If you want to know magnification, you just look at the side of the lens on the microscope, right? So we just take the two pieces that we know that are connected to each other, right? This magnification is what we were using to find this field of view, right? So we multiply those two guys together and we just divide by the other piece, the unknown bit, right? Or the part that we're kind of changing to, right? So this field of view, we did not see using this lens. So we don't put them together, right? We put the two together that came from the same sort of, what's the word I'm looking for there? Same, I don't even know. Lost for vocabulary. My brain's working on the same speed you guys are right now, right? So once we've got this, what is it that we're calculating? We're calculating the field of view of Y. Right? And the reason I'm using X's and Y's is, just say again, X and Y are awesome. Yeah, this is true. What else? In your package, in the package that you guys originally started with, it talked about the low power objective and the high power objective. Why am I using X's and Y's instead of low power and high power? Because it's just algebra, yeah, it just doesn't matter, right? It's just a lower power, a higher power. It doesn't only work from low to high, it also works from high to low, right? It's just math, it's just numbers, right? In the algebra, you can just spin around and flip around and the calculation always ends up becoming the same thing, right? Essentially, if you're looking at this as straight algebra, it's just field of view of X times the magnification of X equals the field of view of Y times the magnification of Y. Right? And you can just rearrange for whichever one you want to isolate to solve.